Good morning. I thought I would do a little Q&A on the problem set that we worked on yesterday in class. In fact, I'll do the first two problems and show you how to do those and what I had in mind. So the problem one, you were given this equation and asked about its graph. So this was supposed to be an easy one. I used X's and Y's here to be more familiar. And this thing has a slope of 5, intercept of 3. The graph is linear. It's a Cartesian equation. There's the graph. All right. So the first problem is to sketch the graph. Hopefully that was a piece of cake. The second one was to find a parametric equation for it. So what this stuff is about is knowing what you've got and what you need to answer the questions. So here's a slope. You have to know what that means. Rise over run, or change in X over change in Y. And you have to know that this is the Y-intercept. So technically speaking, this point is not the y-intercept. The y-intercept is 3, but this point is the point 0, 3. So there's a little difference here. And now the first thing I asked you then, other than the graph, was what is the parametric equation? First of all, this is a line, so we're asking for the parametric equation for a line. What do you need? You need a point on the line, and you need a direction. Now, by direction, I don't mean slope. Direction means a vector. So direction is a vector. So this direction we're talking about will be a vector, and it'll be a vector in the plane because that's where the whole graph lies. So there we go. So what is a point on? Well, you've got the intercept, 0, 3, but you do have a lot of choices there. And now the direction. I gave you the slope is 5. That means that if X changes by 1, Y changes. This is the change in Y over the change in X. You may not show this video to any of my colleagues. I will be castigated. So the change in Y over the change in X is 1, change in Y is 5. So a vector in the direction of the line is 1, 5. And I'll draw that vector first of all here, based at 0, over 1, up 5. So this is the direction of the line. Now, this isn't the line because I didn't place this vector at this point, but if I would have, then this vector placed at the intercept would have been lain exactly on the gold line itself. But that is the direction of the line. So now you're ready to go for the parametric equation. You have to know how these work. This is a function of t, and we're going to look at the range of this function. And it's going to be the point on, 0, 3, plus t times the vector, and I'll just write it as an ordered pair. And then this can be simplified a little bit as 0 plus t is t, 3 plus 5t, and t can be any real number. And this function L maps the real line into the plane. And I wanted to demo that a little bit. If we start with the real number line, that's like a horizontal line. So that's this. Here's the real number line. And what does this function do? this parametric function picks up this line and it places it in the plane. So it does this. And its range means the set of values that you get. The set of values that you get, the range of this function is exactly that line. So in the first case, we graph an equation to get this line. In the second case, we graph the range of this function to get the same line. Okay, so that is the parametric equation. And now I'm going to ask you a few things about it. So let's record L of t again. What was this? T and then 3 plus 5t. And t is a free variable. It can be any real number. And this is the equation. The graph of this equation is exactly the same as the graph of the range of this function. And let's see, find 3 different point slope equations for this line. So now we're talking about point slope. And these are equations, so this will look something like the first thing we've got. And you need to know what you need for this. Well, it's not a surprise. You need a point, and you need the slope. And so we've got the point, 0, 3, and we've got the slope, 5. And so one of the equations is y minus y naught equals the slope times x minus x naught. This is a general form. So y minus 3 equals the slope of 5 times x minus 0. There's one. And actually, that's the same as this one here. And now, where do you have flexibility? Well, you only have flexibility in the point. The slope is 5. That's just a number. That's the slope. So every one of them is going to have an m value of 5. So the only flexibility that you have is the point. And you can get additional points on the line by plug and chug. You can either do x and y, or you can do t here. These both will give you points on the graph, or on the range in this case. So maybe it's easier using the parametric form, but if you plug in 0 for t, you get 0, 3. If you plug in 1, you get 1, 8. If you plug in minus 1, you get minus 1, minus 2. And each one of these will give a different equation, different point slope equation. So this one, using the 1, 8, y minus y naught, is y minus 8 equals the slope times x minus 1. The third equation, using the point minus 1, minus 2 on the line, is y plus 2 equals 5 times x plus 1, minus a minus plus. And there are billions more. In fact, there are infinitely many more. So point slope. And the last one is point normal form. Now, in this case, the things that you need here are a point on, and you need a normal. This normal is a vector. So you need a point on and a normal vector. And then the equation is x minus x naught, y minus y naught. This is a vector in the direction of the line, dot n is 0. So there we go. And so if we find the x naught and and the y naught and the normal will be good. Point on, we already have a billion points on by now. 0, 3, 1, 8, and more. But we need a normal vector. And what does it mean to be normal to the line? I'm going to sketch the graph over here. I hope you can see it just one more time to show that. Here's our line. Here is the direction of the line, 1, 5, I believe, if we remember that. That's the direction of the line. So to be normal to the line, you need a vector that is perpendicular to this one. You need a normal vector, an orthogonal vector, a perpendicular vector. Those are all synonymous for us here. So you need like this guy here. Or maybe this guy here. Those are normal. Those are perpendicular to the direction of the line, and so to the line itself. So these are candidates for n. And what does it mean to be normal? Here you need that the normal dot product with the direction of the line is 0. That's what it means to be perpendicular, is the dot product is 0. So you need to make the dot product with 1, 5, 0. How can you do it? Well, if you check it out, if you reverse these numbers and change one sign, it's going to work out for you. So let's do -5, 1. The dot product of -5, 1 with 1, 5 is going to be 0. And there are plenty of other possibilities here. And now once you do that, then you can write down the point normal form. And so let's see, I'm going to erase this stuff up here. So let's, for our first case, let's take n to be -5, 1. And let's take the point to be equal to 0, 3. Then the equation is x minus x naught equals n, and I'll write this as just an ordered pair again, -5, 1 dot y minus 3. This is a dot product. Let's try this again. X minus x naught, y minus y naught dot n -5, 1 equals 0. So there we go. And then for a second try, we could take the same n or a different n. For example, I could use 5 minus 1. That is also normal to the direction of the line. And the point on, in this case, we could take it to be 1, 8. And that'll give a different equation. So x minus 1, y minus 8 dot this vector this time, 5 minus 1 equals 0. So these are two, and then you can get more. So these are two point normal forms for this. So this is what I had to say about problem number 1. This is the solution. I'll put problem number 2 up separately as a separate video. And so let me see if I can shut this thing off here.